Have you ever fired a rocket at a concrete wall in a video game, only to watch it explode into perfectly uniform blocks that sink right through the solid floor? That clipping isn't an animation error, it's a survival tactic. The game engine is actively panicking and dropping the mathematical calculations required to make the falling debris collide to prevent a total system crash. This specific physics glitch is finally being solved. A new mathematical approach now allows computers to simulate millions of microscopic dynamic fractures in real time. To fix fake digital rubble, researchers had to change how a CPU organizes its workload when processing a chaotic physical event. Developers used a shortcut called Voronoi fracturing because calculating cracks during explosions is too taxing. They mathematically pre-cut virtual buildings, holding pieces together with invisible glue. When detonated, the processor suddenly calculates collision and trajectory for thousands of chunks simultaneously. To keep the game running at 60 frames per second, the computer prioritizes speed over accuracy. It intentionally turns off collision detection for the falling chunks, which is why you see rubble phasing through the floor. This approach fails because it asks a single computational system to process an infinite cascade of overlapping physical interactions at once. Modern gaming computers use multi-core processors, leading to the assumption that throwing more cores at the rubble would solve the lag. In reality, assigning more processing threads to a single chaotic event can actually degrade performance. This diagram illustrates the primary bottleneck, lock contention. Like an army of ants building on the exact same inch of sand, when multiple CPU threads try to update the same memory space, they constantly stop and ask permission to avoid overwriting each other. This communication overhead often takes more time to resolve than calculating the actual gravity and collision physics. Without strict spatial organization, shared processing power inevitably turns into a chaotic bottleneck. The breakthrough solution abandons this shared memory approach for strict spatial isolation. This diagram shows a 3D grid executing a concept called domain decomposition. The environment is sliced into dozens of isolated cubes. We can think of these as 32 grandmasters. Each CPU core is assigned exclusive control over a single grid space. Because these cores own their domains, they don't share memory or wait in line. They instantly calculate millions of microscopic fractures. When rubble crosses a boundary into another grid, the data is handed off smoothly between only those two specific cores. This results in granular, hyper-realistic destruction. Concrete pillars dynamically crumble into fine dust and jagged pebbles, maintaining a stable 60 frames per second. By dividing the environment, researchers proved that isolated zones can handle millions of granular interactions without the lag inherent to unified processors. There is a hidden parallel here for how we process information in our daily lives. We often attempt to operate like the flawed multi-core approach, glorifying multitasking and trying to process every project in a single shared mental workspace. But the human mind suffers from its own version of lock contention. Attempting to handle overlapping inputs at once leads to dropped tasks and mental phasing, the same way a struggling game engine drops collision data. The physics solver suggests a different path. By carving out a specific domain and removing the external noise, you can process incredibly complex challenges without interference. Deep work and isolated focus allow systems to scale, whereas chaotic volume leads to diminishing returns. Mastering isolated focus allows for processing higher levels of complexity without the system-wide lag of a scattered mind. If you want to see more hidden tech insights, hit the subscribe button and remember to keep your domains separated.